Hi, I'm Nato and welcome to the channel. In this video we will be digging into the SQLite main database file header and the informational entries which are used to essentially decode a SQLite database. We won't be covering all entries, but just those that are useful during an examination of a SQLite database. The main database file is where the data from the tables and rows of the database are permanently stored. I say permanently stored, but the table records can be temporarily stored in the journal files before they are committed to the main database file, but ultimately they will end up there. The most common extensions for a SQLite main database file are .db, .db3, and .SQLite, but it is not uncommon to encounter a database without a file extension. Examples of this are Chromium-based web browsers like Google Chrome, Firefox, the new Microsoft Edge browser, and the Brave web browser. Oftentimes it's easier to identify the main database file using its unique header string, which is how our forensic tools identify them during processing. The image on the right has some of the files on the back end of the Brave web browser. You can see at face value only the heavy add intervention opt-out file has an extension. However, there are 4 other SQLite databases in that list that do not have an extension. The file header comprises of the first 100 bytes of the file. These 100 bytes contain 23 informational entries which are used to decode the database. Of the 23, only 14 are useful from a forensic examination standpoint. I will cover all of those 14 entries. All the entries in the header, with the exception of the header string, are big endian integers. At offset 0 for 16 bytes is the UTF-8 header string SQLite format 300. Offset 16 for 2 bytes is the page size. The page size in a SQLite database must be a power of 2 between 512 bytes and 65,536 bytes. Note as the value 65,536 bytes cannot fit as a 2-byte integer, it will instead be denoted as 0001, or big endian 1. Offsets 18 and 19 are 1-byte integers that determine which journaling method the SQLite database uses. Offset 18 is the file format write version, and offset 19 is the file format read version. Both of these offsets will be the same value, with a 1 denoting the database uses a rollback journal, and a 2 indicates it uses a write-ahead log. At offset 20 for 1 byte is an integer value denoting the number of reserved bytes at the end of each page. These reserved bytes can be used by the SQLite encryption extension to store a cryptographic nonce or checksum associated with each page in the database. The only limit to the number of reserved bytes is a usable page must be no less than 480 bytes. This value is useful as it helps us determine the usable size of each page. Offset 24 for 4 bytes is the file change counter. This value is incremented each time the database is updated, aka a transaction has occurred. This is useful when the database uses rollback journaling, as it tells us the number of transactions that have occurred on the database. However, if the database uses write-ahead login, this value will only increment when a checkpoint operation occurs and all active pages from the WAR file are updated in the main database file. Offset 28 is a 4-byte integer that denotes the size of the database in pages. This includes all the 5 different SQLite page types. At offset 32 for 4 bytes is an integer value denoting the page number of the first freelist page in the database. Freelist pages are pages that are not currently in use but may contain deleted records from previous uses of the page. Offset 36 for 4 bytes is the number of freelist pages in the database, which may contain residual data from previous uses. At offset 40 for 4 bytes is the schema cookie. This value is incremented each time there is an update to the database schema. The database schema is what defines the structure of the database, the different tables, fields, indexes, etc. This is important as when there is a schema change, this can break SQLite scripts if column names or storage types change. There is also the chance that additional user data is added to the database when a schema update has occurred on an application. I've seen new tables and columns added to the database that offer a greater insight into the user activity within an application. Offset 52 for 4 bytes determines whether auto vacuuming is enabled on the database. When auto vacuuming is enabled, all free list pages in the database are moved to the end of the database file at the end of each transaction and truncated. This shrinks the main database file, and from an examination standpoint, we lose the ability to recover deleted records from the free list. When this 4-byte value is set to 0, auto vacuuming is disabled, which is the default value. But when the value is a non-zero, it will denote the page number of the largest root B tree page. At offset 56 for 4 bytes is an integer value denoting the encoding for all text strings stored in the database. These 4 bytes can be one of 3 values. When the value is 1, it means all text strings are stored as UTF-8. A value of 2 means UTF-16-LE, and a value of 3 indicates UTF-16-BE. Offset 64 for 4 bytes determines whether incremental vacuuming is enabled on the database. When incremental vacuuming is enabled, only a set number of free list pages are truncated at the end of a transaction. A value of 0 means incremental vacuuming is disabled, and a value of non-zero means it is enabled. Note that if the value is a non-zero, the 4 bytes from offset 52 must also be non-zero. From a forensic standpoint, it is still possible to recover records from the free list when incremental vacuuming is enabled, providing the number of free list pages is greater than the number of pages being truncated. The final entry of importance in the database file header is the SQLite version number, which is stored in the 4 bytes from offset 96. From an examination perspective, the SQLite version number can indicate what SQLite features may be in use. The value in these final 4 bytes of the header are calculated as x times 1,000,000 plus y times 1,000 plus z, where x is the major version number, y is the minor version number, and z is the release number.